So with our last video, we reviewed some basic properties of forces and accelerations and talked a little bit about how forces can act on air masses to influence how these air masses move around in the atmosphere. And we talked in detail about one force in particular, namely the pressure gradient force. But of course, there are other forces. And for our purposes at the moment, the main other force that we're going to be interested in is something called the Coriolis force. The Coriolis force. So that's what we're going to talk about in this lecture. Now, the Coriolis force is a little more subtle than the pressure gradient force. And in fact, in a very strict sense, the Coriolis force isn't really a force at all. Instead, it's what's usually referred to as an apparent force. It's an apparent force. That's to be distinguished from real forces. So it's not a real force. Real forces are things that exert physical pushes and pulls, like pressure gradient force. There's an obvious push from higher pressure to lower pressure. So that's a physical force. That's a real force. In this case, the Coriolis force isn't like that. Instead, it's an apparent force. And it's an apparent force that in this case results from observing a motion from a rotating vantage point. So this is something that arises when we observe motion from a rotating perspective, a rotating vantage point. In this case, obviously, the rotating vantage point would be an observer on the surface of the Earth who is going around in circles. And because he's going around in circles, his vantage point, his perspective on the motion is going to be continually changing as he goes around in a circle. And so as a result, even something that in reality is moving in a straight line, to this person who's rotating around in a circle and sort of viewing it from different vantage points, it's going to end up looking like that object follows a curved path. And so that's what we're really talking about here. It's not actually a physical force. It's sort of an artifact of observing the motion from a rotating reference frame. Okay, now like I mentioned, this is a little bit more subtle than the pressure gradient force, and so I'm actually going to give you sort of two looks at it. The first look is going to be sort of a more basic concepts look at it, sort of a more basic physics kind of idea, and that'll be useful for sort of understanding how this works, that is, how the rotation of the vantage point ends up causing the path to look like it's curved. But it turns out to be a little bit tricky to apply that kind of approach directly to the atmosphere, the rotating atmosphere, or air parcels in the rotating atmosphere. So then we're going to step back and look at this again and sort of appeal to your intuition about how rotating systems work, sort of talking about, rotating figure skaters and things like that. Okay, so with that, let's go ahead and jump into it. So to get started, let's suppose we consider a simple thought experiment in which some object out in space flies past the Earth. For instance, this could be one of these interstellar objects that we've noticed in recent years that some people have proposed could potentially be alien probes that are scanning the planets in the solar system. But regardless, it's just some object out in space that's moving past the Earth. To make it simple, we'll say that it passes directly over the North Pole. Now, as this object is flying along, it doesn't really care about the fact that the Earth is rotating, right? It's not rotating with the Earth, so it doesn't really care about it. It just flies past the Earth. And so to make it simple, we'll just say that the object is moving in a straight line as it goes past the Earth, and we'll say it's going in a straight line at a fixed speed. So to describe the motion, we'll put down some coordinate system, these dotted coordinates here. These are just some coordinates out in space. They're not rotating with the Earth. They're just some coordinates out in space. And we'll say that in this reference frame, in these coordinates, this object is just going to move along the y-axis at fixed speed. So it's just kind of going to do something like this. Just moving along the y-axis at fixed speed. Now, I'll point out that we know, since it's going at fixed speed in a constant direction from last time, we actually know that there's no forces acting on this object in a real sense. Right? There's no force acting on the object because if there were a force, it would cause a change in speed or direction, and since that's not happening, we know that there are no forces acting on it. Okay, now suppose we introduce a second reference frame. So the first reference frame, or our first coordinates here, are going to be the same coordinates as before. We've got these dotted coordinates, which are just the coordinates out in space. We'll refer to these as the stationary coordinates because they're not rotating with the Earth. The way that Newton had posed this, he said that there are some coordinates that are fixed with respect to the fixed stars. He said that there are some stars, the idea is that there are some stars in the sky that don't seem to change their positions. And so Newton used that to define his fixed reference frame, his stationary reference frame. It's just out in space and it's not actually moving. And then on top of that, we're going to have a second reference frame here, the solid reference frame. And this is going to be the reference frame that's rotating with the Earth. So this is the reference frame that, or a coordinate system that an observer on the Earth would see. So this is going to be something that's rotating with the Earth. And so to be sort of concrete about it, I put a couple of reference points here along the axes. I've got New York along the x-axis, and I've got Rome along the y-axis. It just happens that New York and Rome are about 90 degrees apart on the same latitude circle, roughly. And so they make a good pair of cities for an example like this. So we've got our two coordinate systems. Let's go ahead and add a couple observers to observe the motion in these coordinate systems. So in these stationary coordinates, we'll say we have our friend Bob. He's just floating out in space. He's not rotating with the Earth. He's just out there in space, and he's sort of watching this evolve from the fixed reference frame. And then on the Earth, in particular in Rome, we'll say that we have Bob's cousin, Roberto. And Roberto, of course, being on the surface of the Earth, he's going to be rotating around in a circle with the Earth. So to simplify things, maybe I'll get rid of the arrows here. Now, if I step this forward in time, what's going to happen is two things. The first thing that's going to happen is that this object's going to move along the y-axis at fixed speed, just like it did before. And the second thing that's going to happen is that at the same time, the axes associated with the Earth are going to rotate. So it looks something like this. Now, if we ask Bob what he saw from his vantage point, it's pretty straightforward, right? He just saw this object that started along the y-axis, moved along the y-axis toward him at a fixed speed. So we've just got this object that's moving with no forces, and so it just moves in a straight line. Now, but if we ask Roberto what he sees, it's a little bit more complicated because his vantage point is constantly changing as this motion is happening. So let's see if we can tease out what it is that Bob's cousin sees from this rotating reference frame of the Earth. So to figure out what it is that Roberto sees, let's go ahead and plot out the motion as viewed from his coordinates, that is the coordinates associated with the Earth. So here I've got two different perspectives on it here. On the right-hand side, we've got the same thing as before. We've got our fixed coordinates, the dotted line. We've got our solid coordinates with the rotating Earth, and those coordinates are going to rotate. And we'll put one observer, we'll put Bob again in the stationary coordinates out in space, and then we've got his cousin here in Rome that's going to be rotating with the Earth. And on the left-hand side, what I want to do is plot out the motion as viewed by Roberto, right? He's just here in Rome, and he's got his own coordinate system, right? He's got a y-axis that passes through Rome and the North Pole. He's got an x-axis that passes through New York and the North Pole as well. And those are just his coordinates, right? That's what he's measuring things with respect to. So let's plot out what the motion would look like in that coordinate system, the coordinate system associated with Roberto. Let's go ahead and put his cousin, Bob's cousin, over here in Rome. So to be clear, what we're going to do is we're going to look at the right-hand side, which is the same thing we looked at before, and we're going to try to map out where this thing that's flying by the Earth, this interstellar object flying by the Earth, where it is relative to the Rome-New York coordinate axes. So for instance, if we start at this initial time and we ask Roberto, where is this object? He would say that it's some distance from Rome towards the North Pole, past the North Pole some distance. So it's that far along his Rome axis. And then it's going to be some distance towards New York. So it's going to be that far along the New York axis, which means relative to him, he sees the object as being sort of towards the North Pole and off to the left a little bit. That's what he sees. So we're going to go through and then plot that out on the left-hand coordinates, which are his coordinate system. So this is what he sees, right? He sees that the object is some distance towards the North Pole and a little bit past it. So the same thing as over here, just plotted on his axes. And then it's some distance towards New York. So I've plotted it as some distance towards New York over here. And so he sees it as being towards the North Pole and off to the left a little bit. So I've just mapped the position relative to his coordinates over to these axes. And that's what we're going to do. We're going to do that at each of the times associated with the motion. That is, we'll step this forward, we'll see where it is relative to Roberto's axes, and then we'll plot it out over here relative to his coordinate system. All right, so let's erase these arrows to get started. So we've already got it at the initial time. So let's step it forward one. And we see that the object moved along the y-axis in the stationary coordinates, and the Earth rotated a little bit. So now if we ask Roberto, where is this guy? Now he's going to say, well, it's some distance past the North Pole on the Rome axis, and a little bit towards New York, but not that far. So if I plot that out over in his coordinates, it's some distance past the North Pole on the Rome axis, and a little bit towards New York. So that's where it is relative to his coordinates. We step it forward again. And now we ask him where it is. And so it's going to be some distance past the North Pole, not very far, and then just a little bit off towards New York. So I plot that out his coordinates along the Rome axis, along the New York axis, just a little bit towards New York. And so that's where it is relative to his coordinates. Step it forward again. Now everybody agrees it's over the North Pole. The coordinates line up. Step forward again. So the coordinates rotated. So now if we ask Roberto where it is, it's not quite towards the North Pole and a little bit off towards New York. So it's not quite to the North Pole and a little bit off towards New York. And so we're doing that at each of the times, right? So we do it again at the next time, plot out where it is relative to his coordinates. So it's right there, and then so forth and so on. Okay, so now that we've plotted out these positions as viewed relative to Roberto's coordinates, let's go back to the beginning here and run it through again. And pay attention to the left-hand side where we've plotted it relative to the earthbound coordinates here, and ask what it looks like to an observer in this coordinate system. So let's go ahead and step it forward here. So what do we see? Well, we see the object comes into the axis, and then it rotates away. Let's go ahead and do that again. So it kind of follows this curved path coming into the origin and then rotating off to the right. So kind of like this. Maybe one more time. Now, if we ask Roberto what he sees in his coordinate system, he's going to tell us that he saw the object following a curved path, kind of like this, coming into the origin and then curving away. And this curving of the path, as seen by the observer in the rotating coordinate system of the Earth, this apparent bending of the path is what we refer to as the Coriolis effect. And this kind of causes a problem if we want to describe the motion in the framework of Newton's laws, because remember, according to Newton's laws, an object only changes speed or direction if there's some force acting on it. Yet here we've got a case where there was no real force acting on it, but yet the observer in the rotating system sees the path as bending. Now again, there's not really a force involved, but he sees the path as bending because his vantage point is constantly changing. But what this means is that if we want to describe the motion using Newton's laws as viewed from the rotating coordinate system, we'll have to introduce some force to describe this motion. That is, we see the motion as being accelerated, so we're going to say that there's got to be some force associated with that. And this force that we introduced in order to account for this bending of the path is what we refer to as the Coriolis force. Right, it's an apparent force whose role is simply to account for the bending of the path as observed by the observer in the rotating coordinate system. So for instance, if I were to step this forward, we'd see the object coming in to the axis. Right when it gets into the origin here, so it's directly over the North Pole, right when it gets to this point, the motion is actually tangent to the y-axis, which means the velocity, the motion of this object at this point, is actually directly along the axis, right? It's coming in from the right-hand side, and then it's going to bend off to the right, but just at this transition point, it's moving directly along the y-axis. So its motion is actually directly along the axis. And then in order to get the path to bend, according to Newton's laws, we would have to have some force that pulls it to the right. So what we're going to do is we're going to introduce some force, namely the Coriolis force, whose purpose is to account for this bending of the path as seen in the rotating reference frame. And the direction of this Coriolis force is going to have to act along the x-axis, right, to the right, in order to pull the path off to the right, to cause it to bend. So that's what our Coriolis force would do, is cause that bending of the path. And then it bends on the path, and off it goes. So that's the basic idea then. So the Coriolis force is this apparent force whose role is to account for the bending of the path, as seen by the observer in the rotating reference frame. The idea being that if we were to ask Bob why it was that the path was bending, he would tell us that the path was bending because there was this apparent Coriolis force that acted on the object and caused the path to bend, right? So the Coriolis force accounts for the bending of the path as seen in the rotating frame. Okay, but that said, it turns out to be a little bit tricky to apply that kind of basic principles perspective to understand sort of at an intuitive level what's going on with air parcels in the atmosphere. So in order to see that, to sort of build up some intuition for that, I'm going to back off and look at this from a slightly different perspective. In particular, I'm going to sort of more directly appeal to our intuition about how rotating systems behave. So to be concrete, let's suppose that we have some object that's following a circular path, rotating around some central axis of rotation. So for our case, this would be some small mass of air in the atmosphere that's rotating around the Earth's axis, so some small air parcel. So some small mass of air we refer to as an air parcel. So an air parcel is a small mass of air. And so we've got some parcel of air that is circulating around the central axis of rotation. And let's try to think about some properties of this rotation, things that sort of should hopefully be familiar from stuff that you guys have seen before. So, first property. The first property is if you have some system that's rotating around an axis, then as that object moves closer to the axis of rotation, it comes in closer to the axis, then its rate of rotation will tend to increase. That is, it'll start to spin faster. Sort of the classic example that everybody gives for this is the example of a figure skater, so as shown here. I'm sure you guys can appreciate my artwork here. So we've got a figure skater, so we've got two cases of a figure skater. So let's say on the left-hand side, we've got the figure skater and she's executing a spin. But she's got her arms out and she's got her leg extended or knee extended. And so she's spinning, but she's not spinning all that fast. And then, of course, when she pulls her arms in, as in the second frame here, and pulls her knee in, she's pulling more of her mass in towards the axis of rotation, right? The object is moving closer to the axis of rotation. And as she pulls that mass in towards the axis of rotation, she starts to spin faster. as suggested by the thicker lines here. So as she brings her arms in towards the axis of rotation, she starts to spin faster. So the skater rotates faster about the axis. So this is a general property. It's usually stated as a consequence of something called conservation of angular momentum, but you can really just think of it as a consequence of Newton's laws as applied to a rotating system. But regardless, this is how it works. If you pull the mass in towards the axis of rotation, it'll start to spin faster. Perhaps an example that's a little bit more directly like the kind of thing that we're thinking about is if you have rotating water moving towards a drain, right? So if you have water that's rotating slowly about a drain, and then it gets pulled in towards the drain, as it gets pulled into the drain, it starts to spin faster and faster and faster. It's the same kind of idea. As you take the mass and move it towards the axis of rotation, it starts to spin faster. So that's the first property. When something moves towards the axis, it'll spin faster. In order to see how this applies to air parcels, small air masses in the atmosphere, we first have to think about the direction of rotation for the Earth. So in the case of the Earth, the direction of rotation turns out to be west to east. So what I mean by that is if we're looking at the Earth and we've got the sort of west coast of the US over here, if you like, where I put W, and the east coast of the US over there where I put E, then the sense of rotation is that the west is sort of chasing the east here, right? So it rotates in such a sense that west follows east. If you were to look at this from above the North Pole, from a vantage point up here, you would see looking down on this rotation, it would look like it's rotating counterclockwise. So that's the sense of rotation of the Earth. And what this means is that if you, relative to an observer at the ground, if you have some object, some air mass in the atmosphere that's rotating faster than the Earth, right? So if it starts spinning faster than the Earth, an observer at the ground on the surface of the Earth would see that as a motion towards the east, right? If it's spinning faster than the Earth is spinning, then relative to an observer on the ground, it would look like it's moving towards the east. It's kind of like if you're out on the highway and some car is going faster than you are, it'll look like that car is moving in the direction, towards the direction that you're going. It's the same kind of idea here. You've got an observer on the Earth who's going around the Earth's axis, spinning around in a circle, but if you have some other object that's rotating faster, then relative to the observer on the ground, it would look like that object is moving eastward. And by contrast, if you had some object that was rotating more slowly than the Earth, then it would look like it's falling behind. And so then in that case, it would look like it's moving westward. So objects rotating faster than the Earth look like they're going eastward. Objects that rotate more slowly than the Earth will fall behind and look like they're moving westward relative to an observer on the Earth's surface. Okay, now let's suppose that we think about, in particular, some air parcel, some small mass of air in the atmosphere that's moving northward. So it's moving northward along one of these longitude circles here. I.e., suppose we have a northward wind that's moving the air mass northward. Now, as this air mass moves northward, it's going to actually be getting closer to the axis of rotation, right? And eventually, if it goes all the way northward, it's going to be at the axis of rotation. So little by little, it's going to be moving in towards the axis of rotation. And because it's moving towards the axis of rotation, we expect it to start spinning faster, which relative to an observer on the ground would look like the object is starting to move off towards the east because it's spinning faster than the Earth. So, to an observer on the ground, an air parcel that moves northward, an air parcel moving northward, will appear to bend off towards the east, right? Because it's going to start spinning faster than the Earth, and so it's going to appear to bend off towards the east. That is, it's rotating more quickly than the Earth is. So if I were to draw that out on the globe here, then I would have an air parcel that's moving towards the pole, and it starts to spin faster than the Earth, and spinning faster than the Earth because it's moving towards the axis, right? It moves off along the north, moves towards the axis. As it moves towards the axis, it starts to spin faster, and spinning faster makes it bend off towards the east, right? It's spinning faster than the Earth. And of course, if we had the opposite, if we had an air parcel that was moving southward, then in that case, it's moving away from the axis, and so it's actually going to rotate more slowly. And rotating more slowly looks like it's falling behind towards the west. So that's the opposite case. A parcel that moves southward will appear to be bending off towards the west, which in reality just means it's rotating more slowly than the Earth about the axis. So if I draw that in on my picture of the globe here, that means I have a motion, an air parcel that's moving southward, and as it moves southward, it bends off towards the west because it's going to start rotating more slowly. It's getting further from the axis, so it starts rotating more slowly. Okay, so that's the first kind of effect to think of, moving towards the axis and rotating more quickly. And that accounts pretty well for what happens when parcels move northward and southward. To describe what happens to air parcels when they move east or west, we have to consider a second property, very closely related property, but a slightly different property. And that's this. So suppose, again, we've got some object that's rotating around some axis of rotation like before. And suppose in this case we take that object and we speed it up. We accelerate it so it starts to spin faster than it was before. What do we expect to happen? Well, as the object speeds up, what happens is that it will tend to move away from the axis of rotation. It'll tend to slide outward away from the axis of rotation. Hopefully this should be somewhat intuitive, but you could think of this, for instance, in the case of if you had a bungee cord, so an elastic cord, and you stuck a ball at the end of it, and then you start swinging it around over your head. Or if you have a slinky, you could do the same kind of thing with a slinky, start swinging it around over your head. And so first, over here on the left-hand side, let's suppose that you take that bungee cord with the ball at the end and start swinging it kind of slowly, just fast enough to sort of keep it up and form a circle, rotate around the axis above your head. And then you take that ball and you start to swing it faster and faster and faster. What do you think is going to happen as you swing this guy around faster? Well, what's going to happen is that the ball is going to move away from the axis of rotation. It's going to move out to a larger radius as it spins faster, and the bungee cord is going to end up being extended. So swinging the ball faster will cause it to move outward, away from the axis, which in turn has the effect of extending your bungee cord. So this is kind of a general property. If you have something that's rotating around an axis of rotation and you speed it up so it's rotating faster, it's going to want to tend to slide out towards a larger radius. It's going to want to tend to slide away from the axis of rotation. Now, when we apply this idea to the atmosphere, we have to be a little bit careful because in the case of the atmosphere, air parcels are more or less going to be constrained to follow the shape of the Earth, i.e. to move more or less parallel to the ground. This is for a couple reasons. One is just that the atmosphere is very thin compared to the size of the Earth. So when objects are moving around, in order to stay in the atmosphere, they're basically just following the shape of the Earth. So moving along, following the shape of the Earth. But a second, actually sort of more fundamental reason is that in order to move outward away from the Earth, the air parcels would have to counter gravity. And it turns out that gravity and in the pressure force that we talked about that holds columns of air up against gravity, those forces are much bigger than the kinds of things that we're talking about here associated with the rotation of the Earth. And so as a result, we don't really get a whole lot of motion in the vertical direction due to these kinds of effects because they're just going to be washed out by gravity. So as a result, we're really just thinking about the horizontal motions following the surface of the Earth, following the shape of the Earth. So however you want to think about that, that's basically what happens is that the air parcels are going to be constrained to follow the shape of the Earth. So what that means is if an air parcel wants to move out towards a bigger axis, move away from the axis of rotation, the only way it can move outward away from the axis of rotation is to slide southward, right? It's going to have to go southward in order to go towards a larger axis, move away from the axis of rotation. And by contrast, if it's going to move inward towards the axis of rotation, the only way to do that is to move northward, following the shape of the Earth. So we're constrained, if we're changing our radius, we're constrained to follow the shape of the Earth, which means northward or southward. Okay, now let's suppose that we have some air parcel that's moving eastward. So it's moving along a latitude circle eastward relative to an observer at the ground. Well, again, moving eastward relative to an observer on the ground really means that it's spinning faster around the axis of rotation than the Earth is. And something that's spinning faster than the Earth is naturally going to slide out towards a larger radius, which means the only way you can do that is to slide southward, right? That's the way you get away from the axis of rotation. So what that means is that to an observer on the ground, an air parcel moving eastward, which means it's rotating faster than the Earth, is going to want to slide southward, will appear to bend southward, appear to bend to the south, so as to be able to move outward from the axis of rotation towards a larger radius. Right? So it's moving eastward, which means it's rotating faster than the Earth, and because of that, it wants to go away from the axis of rotation towards a larger radius, and the only way to do that is to bend southward, taking you away from the axis of rotation. By contrast, if you had an air parcel sort of doing this in reverse, if you had an air parcel that's moving westward, that means that it's spinning more slowly, and objects that spin more slowly get pulled in towards the axis of rotation. It's exactly the opposite of the bungee cord example. So if we start to rotate more slowly, we actually want to move in towards the axis of rotation towards a smaller radius. So an air parcel moving westward, rotating more slowly than the Earth, will tend to bend towards the north, because that's how you get in towards the axis of rotation, towards a smaller radius. Right, towards smaller radius. So sketching that on my globe, we've got an object that's going to be moving westward, and as a result of moving westward, it's rotating more slowly, so it moves in towards the axis of rotation. Kind of like that. So we've kind of done all the cases here. We've done northward, southward, eastward, and westward. If we put it all together, then it looks like this, right? So these are our four cases. An object moving northward towards the axis of rotation gets pulled towards the east to spin faster. An object moving towards the east slides towards larger radius, which means it goes southward. An object going southward bends westward. An object going westward bends northward. So those are each of the 4 cases. Now you'll note that in each of these cases, our parcel ends up deflecting to the right relative to the initial direction of motion. For instance, in this case here, it started off going northward, but then gets pulled to the right relative to its initial direction. This guy started off going eastward, but again gets pulled to its right relative to the initial direction, and the same for the other 2 cases. So what this means then is that in the northern hemisphere, which is the case we've been doing, in the northern hemisphere, the Coriolis force always pulls to the right of the wind direction. Right? The wind direction is the direction of motion, and the Coriolis force is always going to pull us to the right of that wind direction. i.e. it's going to pull us perpendicular to the wind direction to the right. So for instance, if I had some wind that was blowing in this direction, if that was my wind direction, then the Coriolis force is going to pull us to the right of that direction. And more specifically, what I mean by that is if you are looking in the direction of the wind, right? If you put yourself in the figure looking in the direction of the wind, then it's going to end up pulling to your right. And to the right would be this direction. So the Coriolis force is going to act to the right of the wind direction and cause it to bend. So that's a general property then of the Coriolis force in the northern hemisphere. But we have to be a little bit careful, because if we went through and repeated all of these arguments about angular momentum and so forth and so on, and applied them to motion in the southern hemisphere, we'd end up finding that everything pulls to the left instead. Everything's going to end up bending to the left. So in the northern hemisphere, everything bends to the right, but in the southern hemisphere, it actually switches, and everything is going to bend to the left. Now in this class, we're basically, unless otherwise stated, we're always going to be doing the northern hemisphere, so we'll focus on that case. But you should keep in mind that in the southern hemisphere, it bends the other way. So that's the basic idea, but there's 2 more properties of the Coriolis force that we need to be aware of. And the first property here is that this Coriolis effect that we described depends on the latitude. There's a latitude dependence here. And probably the simplest way to think about this is to see this is to think about what's going on for an air parcel at the equator. So if we have an air parcel at the equator and it moves northward, well, when it moves northward, it actually ends up moving directly parallel to the axis of rotation. So it's not actually getting any closer to the axis of rotation, which means this effect of moving in towards the axis and spinning faster isn't happening. And so there's no deflection. There's no deflection of this parcel here at the equator. Similarly, if we had an air parcel moving eastward, well, it would want to slide out towards larger radius, but it can't. It's constrained to follow the shape of the Earth, so it can't move off of the surface of the Earth. There's no way for it to go to larger radius, and there's no deflection. So the moral of the story is we don't really see this Coriolis deflection at the equator, which by extension means that the associated Coriolis force is 0 at the equator. By contrast, if you think of a parcel up near the poles, well, as this parcel moves northward up near the poles, it's more or less going directly in towards the axis. And so it's changing its radius very quickly, coming in towards the axis quickly. And so it's going to see this effect of speeding up and bending to the east. So you get the strongest effect of the Coriolis then up near the poles, where you change your radius quickly, and you get 0 effect down at the equator. So, moral of the story, conclusion from that, is that the Coriolis force is strongest near the poles. So the Coriolis force is strongest at the poles, and it drops to 0 at the equator. Strongest at the poles, and it drops to 0 at the equator. And in between, you have some dependence on the latitude, where it goes from its biggest value at the poles and then gradually decreases until dropping down to 0 at the equator. It actually varies, to be quantitative about it, it varies with the sign of the latitude, but there's just some dependence where the strength of the Coriolis force gets bigger the closer we get to the poles. Okay, so that's the first property. There's a latitude dependence. The second thing we need to be aware of is that it also depends on the wind speed. And it's kind of for a similar reason. So again, if I think about a parcel moving northward here, as it moves northward, it goes towards the axis of rotation, and pulling it in towards the axis of rotation causes it to spin faster and bend towards the east. Well, the strength of this effect is going to be bigger if we're changing our radius more quickly. That is, if we're moving more quickly towards the poles, if we have a bigger wind speed, then we're going to have this effect happening more quickly. And it's going to be a stronger effect, right? We're going to be coming in towards the axis more quickly, and that's going to give us a stronger bend to our path. Whereas on the other hand, if we're moving in towards the axis more slowly, then the change in our radius is going to be smaller, and so the bend in the path will end up being weaker because of that. Right? We're not going in towards the axis as quickly, and so we end up bending more slowly. So the net result of that kind of argument, the conclusion here, is that a stronger wind will result or be associated with a stronger Coriolis force, a stronger bending of the path. So stronger winds are associated with a stronger Coriolis force. So for instance, suppose that we had some wind that was moving in this direction as looking down from above. So it's moving northward, say. And then we've got some other air parcel that's also moving northward, but more slowly. Well, for this first guy up here, so recall that the Coriolis force pulls to the right of the wind direction. So if we're looking in the direction of this wind, the direction to our right would be this way. So that's the direction of the Coriolis force. This guy down here having a weaker wind, it'll also have the Coriolis force pulling to the right, but since the strength of the Coriolis force varies with the wind speed, the strength of the Coriolis force in this case will be smaller. So we get a smaller Coriolis force out of that case. Okay, so that is everything. So let's see if we can put all this together here, summarize all the basic properties. So summary, basic properties of the Coriolis force. So first, the Coriolis force is an apparent force, and its role is to account for the apparent deflection or bending of the path as seen by an observer in the rotating reference frame. Now, the second point is that in the northern hemisphere, the sense of this deflection of the path is always to the right of the wind direction. That is, if you're standing and looking in the direction of the wind, then the Coriolis force is always going to pull to your right, to the right of the wind direction. The size of the force, the strength of the force depends on the latitude, with the strongest force, Coriolis force at the poles, and zero Coriolis force at the equator, and in between varying between the two. And then finally, the force also depends on the wind speed, with stronger winds associated with stronger Coriolis force. All right, so that's our overview of the Coriolis force. We'll leave it there for now.